original example with a very small economy with steel, food, and labor as the only sectors of the economy, and we're going to come up with a solution like this, okay? And this same idea can be used for any kind of input-output model for any size, certainly, for any kind of economy. And you can see it has a lot of very interesting applications to it. Now back to our original problem. What if we ask the following question, right? We have a certain demand. How much steel, food, and labor should be produced in the economy to satisfy a demand for 200 units of steel, 100 units of food, and 100 units of labor? Very interesting question. And using the basic input-output model that we've constructed, knowing the amount that's required as an input for all of these sectors, we could answer this question very easily. Okay? And of course, using our understanding of matrix equations, it becomes a fairly straightforward problem. So the first thing is, let's create the demand matrix for this. The demand matrix is going to be a column matrix, a 3 by 1. So in this case, my demand matrix is going to be, well, again, remember that my first column corresponds to steel, the second is food, and third is labor, based on how I developed my matrix earlier. So the demand matrix in this particular problem is going to be 200, 100, 100, right? Just encapsulate all of that information into one matrix, okay? Keeping in mind the units for later. So that's my demand matrix. And really, to solve this question, I simply have to solve the corresponding matrix equation, which is the following. Here's my net production, x minus ax. That has to equal d, right? In order to actually satisfy this, what's the minimum amount of steel, food, and labor that should be produced to meet this demand, right? So to meet the demand means to be equal to the demand. And so, again, what we're going to do is we're going to solve this using the usual notion of matrix multiplication, provided we remember how to construct an inverse. So what I can do is I can factor an x out of this. I'll factor it that way, just to make the directions the same way we dealt with before. If I factor an x out like I do real numbers, again, x, of course, is a matrix, I can write this as I minus a multiplied by x is equal to d. And now what I want to do is I'm looking for x, right? The unknown is x. Okay, x is what? Just like before. And so the x is my, again, the amount that's produced. That's my production matrix, x. And I want to know how much to produce. So in order to actually isolate the x by itself, remember that I multiply by the inverse of this quantity right here on both sides. So whatever I do to one side, I must do to the other. So I multiply both sides by I minus a, which is the inverse of that, I should say. And of course, I minus a is really the same size as a. It's some kind of matrix, n by n matrix. So this is an inverse multiplied by I minus a multiplied by x is equal to the inverse of this multiplied by d. Okay, so this is going to be the inverse of this, which is I minus a inverse multiplied by my demand matrix. Okay, and now, of course, multiplying these two together, this is just a matrix and this is just a matrix. You're just going to get the identity, right? The identity of size I minus a, whatever that size is. So you're going to get an identity matrix multiplied by x is going to be just equal to I minus a inverse is d. Okay, and again, remember that I've erased d, but your demand matrix here is 200, 100, and 100. Okay? So let's do all of this with actual numbers in them, and we'll find the solution to this particular question. All right, I'm back to my problem, and I've written back down what my input-output matrix is. Here it is. Here's my production matrix, steel, food, and labor, and my demand matrix. Okay? So now the first step is to come up with what is I minus a, right? Well, we just take the difference between two matrices. I is my 3 by 3 identity matrix, and a, of course, is my 3 by 3 input-output matrix. So when I take the difference here, this is the value I get. Okay, so 1 minus 0.4 is 0.6, 0 minus 0 is still 0, 0 minus 0.1 is negative 0.1, and so on. Right? Remember that we simply subtract every single element from every other element from the two matrices. So there's my I minus a. So let's go ahead and now take this and put it into my matrix equation to actually solve the problem. So now putting all of this together in an actual equation here we have the, again, surplus matrix is equal to the demand. I want to know how much should I produce, right? What should it be each individual part of the production matrix in order to meet the demand that I have. Again, what I did is I factored out an x here, so I have I minus a, which is again another 3 by 3 matrix, is equal to d, the demand matrix. Okay, here's how I solve. Well, we already computed I minus a. Here it is, right? That's a 3 by 3 matrix multiplied by my x, which is production matrix. And I want to, these are my unknowns, right? How much should I produce of the steel, the food, and the labor? And here's my demand that I'm looking to meet. Then, of course, here's the next step, which is I multiply both sides of the equation by the inverse of this, because I want to isolate x by itself. So here's the inverse multiplied by this side, and here's the inverse multiplied by that side. Again, it's a 3 by 3 matrix, so I can compute the inverse, and we know how to do that. Then, of course, when I multiply two matrices, its inverse, when I take one matrix and multiply it by its inverse, I always get the identity. Here's the 3 by 3 corresponding identity multiplied by x is equal to the inverse of this. Now, you should go and you should compute. This is what I get for the inverse of I minus a, or the inverse of this. Okay, it's a whole lot of kind of strange fractions, but we know how to compute these. It's not so bad. That multiplied by the d, or the demand matrix. So once I've multiplied these two together, again, this is a 3 by 3, this is a 3 by 1, I know I'm going to get a 3 by 1 column matrix out. And so when I do that, again, I take this product plus this product plus this product is this first term, this product plus this product plus this product is the second term, and so on. And I get this column matrix out. Okay? And this is what I have for the production matrix. Once I multiply, of course, this 3 by 1 matrix by this identity matrix, I get, of course, this same column matrix back out again. And what does this say, right? What is the actual end result? It says that in order to meet demand, the demand of 200 units of steel, 100 units of food, and 100 units of labor in this particular economy, it means that the steel sector should produce at least 628.51 units. So 628.5 units of steel. We need to produce at least 1,685.7 units of food. So 1680, let's round up to 86 units of food. All right? And finally, we have that this says that in order to meet this demand, we must produce at least 1,771.4 units of labor. Or maybe we'll just round that to 1,772 units of labor. We can't have fourth of a person, right? So we probably want to at least go up to the next unit. But the point is, depending on how we round this, which is up to the particular problem, this gives me the answer, right? Given some demand matrix, how much should I produce in each sector in order to meet that demand, knowing that part of the production is consumed by the production process itself. Very interesting. And again, this very simple model has a wide-ranging application. It's used by many countries to actually plan ahead as to how much should be produced for each sector. And also it's a way to plan ahead to estimate what the GDP of each year might be, whether you're having growth or not. Okay, so very applicable, very useful. And again, its power and its applicability is in its simplicity. It's very simple. The mathematics is simple. We've already learned all of the processes necessary. The most difficult part when computing this kind of problem, when working on this kind of problem, is to actually convert the problem into a mathematical statement, right? That's usually the hardest part. But once you've done that, we know how to actually solve matrix equations. So this is an example of an input-output model, a particular example of trying to meet a particular demand.